In this presentation, we're going to look at Markov chains. So the first question asks us to explain what is meant by a time homogeneous Markov chain. This is actually just a sort of quick definition, just to sort of counterpoint stuff that I have coming up later on. So this is going to be a short enough presentation, but it will sort of compare with other presentations where I make things a little bit more complicated. So it's good to know the difference between one and the other later on. Consider time homogeneous two-state Markov chain with the transition matrix A minus B, 1 minus A, B, and 1 minus B. Okay. Explain the range of values that A and B can take, which would result in this being a valid Markov chain, which is irreducible and also periodic. In one case irreducible and in the other case periodic. So just actually to start off, a Markov chain is a stochastic process with discrete states operating in discrete time. Okay, so that's actually pops up every so often. It's discrete state space and discrete time space. That's actually an important little part of this, and so it's always important to distinguish that as a Markov chain, as the characteristics of a Markov chain. With the probabilities of moving from one state to the other are dependent only on the present states of the process. Okay, so if the transition probabilities are also independent of time. Okay, so that's time homogeneous. Okay, so another way you could sort of say it is if the n-step transition properties are dependent only on the time lag, the chain is said to be time homogeneous. Okay, just where they just on basically just on the last state it was in. Okay, so if it's in state A, what's the probability of being in state B? Okay, time homogeneous means that they're consistent as well. They're consistent from one state to the next. Okay, and it just so heterogeneous is where things get a bit more complicated. Okay, so the time homogeneous is a sort of the simple, straightforward case. Okay, so what we want to do is have this chain that this is going back to that matrix. Let's actually just draw it out. Actually, A, B, and A, 1 minus A, B, and 1 minus B. This is our transition matrix. Okay, and essentially what we want is an irreducible matrix. Okay, so in the case where the chain is irreducible, that means if in the case the chain is irreducible if the transition probability out of each state is non-zero. Okay, or equivalently, it's possible to reach one state from the other. Okay, so essentially we're allowed to go from state A to state B. We can transition back and forth without any difficulty. Okay, so for that to happen, what also can happen here is that they can just stay in their own states as well. Okay, so they can stay in their own states with probability 1 minus A and 1 minus B, or they can transition across from one to the other with probabilities A and B. Okay, now I probably really shouldn't have used A and B to describe the states. I probably should have gone for something like X and Y. Okay, so X and Y. Anyway, so that's just straightforward enough. So what can also happen is it can just remain in one state, or stay in one state from one phase to the next. That is possible. Now, a chain is periodic if the chain must alternate between states. Okay, so what happens here in this case is that they have to go back and forth from each other. So it goes from X to Y and back. So it transitions from X to Y, and then when it's in Y, it must transition back to X. And in this case, we have a period of 2. Okay, so for that to happen, the transition matrix must look like this. Okay, it's just toggle back and forth. If it doesn't, then it means it can stay in state X for a while and then transition to Y, or otherwise be in Y and stay in Y for a while and then transition to X and so on, which means it's not periodic. So that's it there. That's we leave it there. That's just a quick definition to get started.